Good morning. I am Krishna Kumar. Let me conclude the discussion on inverse function theorem with an example, which goes into all aspects of the theorem. So let us straight away go into the example. So we have two copies of R2, and we define equal to now let us designate the domain space as xy space and the range space space. Let us write then what you have is phi maps now you know that with the usual R2 considered as the usual metric space, uxy is a polynomial, so also vxy, therefore they are smooth functions. Now let us look at the derivative. Now you see that the phi derivative at xy is a linear transformation from R2 to R2. Okay. So this with respect to the ordered basis E1, E2 is given by with respect to E1, E2, And this in this particular case turns out to be it's a linear transformation from R2 to R2. Now you see that the rank of is equal to is equal to 2, that is phi prime is invertible if and only if now this is the observation that we make. That comes from here. The determinant of this is equal to 0 if and only if x square minus y square equal to 0. That is determinant of this. So now it is time we had some diagram. So this is the scenario. This is the xy plane and this is the UV plane. Now we see that phi is defined on the entire xy plane. And x square equal to y square is this line, x equal to y and x equal to minus this pair of lines passing through the origin correspond to so this is x equal to y, this is x equal to x. So in the complement of this pair of lines, phi is differentiable. And phi is a map defined from here. Okay. So the domain of phi let us, what is range of now this is to be analyzed properly and that makes things interesting. It's not equal to the whole of UV plane because you see that x square plus y square greater than or equal to 0 implies u is greater than or equal to 0. Therefore, u less than or equal to 0 is not in the range. Okay. Moreover, you see that you have u minus v equal to two xy whole square. Therefore, you see that u minus v is positive. So also u plus v whole square. Therefore, equal to 0. And you know that u is positive, so you know u is greater than or equal to 0. Together with these results, it implies that mod v less than or equal to or I can write it more specifically, that is u is greater than or equal to v. Now let us take v positive, then u is greater than or equal to v. Let us take v negative, then u is greater than or equal to minus v. So that gives this. Okay. So from this we conclude that u is mod v is less than or equal to u. So what is that? So this is v equal to u and v equal to minus u. So you have u greater than or equal to 0. This is the region. This is u equal to v minus v. And one observes that is uv range of phi is contained in that is this marked region. So the range is contained in that. Okay. Now what we need is the following. Is the range equal to this set? So let me call this I can more explicitly write. Then is equal to u. So what you have to do is you have to take some uv belonging to v and then show that there is a corresponding xy which gets mapped to it. Okay. So Let us do it separately for uv non-negative. Of course, u is non-negative, v is non-negative, and v negative. So both the cases. Okay. Then what you have? Then you see that, see, you have, in any case this is true, u minus v equal to x minus y square. Therefore, u plus v. Now let us see what we want to show is that this is just all. Therefore, you don't have to work too hard. Right? Okay. So let us take two regions. Now this is mu. Now I call this part V plus. Now we make the following observation. Let V is as defined here. It's a definition. And V plus we have defined here. Okay. So these are the notations. Now UV belonging to V plus. Now we want to show that there exists an XY corresponding to this. Okay. Then what do you have? You have, see, u minus v has to be positive, u plus v has to be positive. U plus v, there is no problem. Therefore, you have two equations, namely x minus y let us take the plus sign. This is well defined, and so also u plus. So that gives x is equal to, add the two, well defined, plus y equal to now these are meaningful because of our condition that this belongs to. Okay. Now they are real numbers, and this is so we observe that there exists such that phi of s. That's clear. Now similarly, you take the case choose. Again, you see that what you have is v is negative, therefore mod v is, see what we have is that mod v is less than or equal to x. So v is negative, therefore this is u minus v is well defined, and v is negative, but you have this condition, therefore this is true, therefore y is also equal to or once again you have the same definition, y equal to v is negative, therefore this term is positive certainly. V is negative, but you have this condition that mod v is less than u, therefore this is well defined. Therefore there exists so you see that phi is on P. What we have shown is that there exists at least a pair xy which gets mapped to the given uv in V plus. Outside that, the question does not arise at all, because you see that the range of phi is contained in V. So we are showing that for each element in V, we have shown that there exists a corresponding xy in R. So this we have proved. So the range of, therefore range of phi now we also make certain observations. The observations are, okay, what about these numbers? Let us work it out. Okay, you see that if uv belongs to V plus, what can you say about x? Implies, see, x is positive, y is also positive, because you see that this is certainly less than this, because we are taking the positive square root on both sides, and this is certainly less than that. Therefore you have, this implies uv belongs to V plus, implies first quadrant. Both x and y are greater than or equal to 0. That is, since x is greater than or equal to 0, that is the result. What happens when uv is some point here? That is, v is negative, but certainly mod v is less than or equal to mod u. If that is satisfied, then what happens? Let us look at this map. X is, then suppose v is negative, now you see that this is positive. So this is positive, and what about this? This is also positive. Therefore x is again positive. Okay. It's a very elementary thing, but certainly worthwhile for the students to put their hand on and understand it properly. Now you also see that implies, look at the definition of x, x is greater than 0. And what about y? You see that v is negative, therefore the magnitude of this is greater than the magnitude of this. Therefore, y is negative. Okay, which implies fourth quadrant. Okay. Now you also observe one more thing. What about x here? X is certainly greater than or equal to y. So here, this definition, see that x is greater than or equal. Okay. So what about uv belonging to v minus? What about x? See, v is negative. Then what happens? And y, what about the value of y? Y is negative. Okay. But if you take mod y is negative, therefore take mod y, then you see that equal to 0. That is there. And mod y is less than x. Therefore, you see that it is this particular wedge shaped portion which gets mapped into. So let me call this one. Okay. Mod y So what you have is that if you have a point here, this point goes somewhere here. You have a point here, this goes somewhere here. This is the kind of mapping that takes place. Okay, right. Now we make some observations. First, observe that phi is not a one-to-one map. We shall observe that not fun. That's quite easy to prove because you can find so let us start with some element in V plus. So you show that there are more than one point which, so this comes from the following. If why is it so? It's quite easy. Therefore, it is not one-to-one. So for every xy that gets mapped to UV, minus x minus y also gets mapped to. Okay. Therefore, this is not one-to-one. So let us consolidate what we teach. So if your xy happens to be in W1, then minus x minus y happens to be in the third quadrant, but on this portion. Here, because you are just drawing the line and then doing this. So this is, if this is xy, you see that minus x minus y. This is minus x minus y. Okay, and if it is over here, then it is going to be in the second quadrant. Okay, so you see that corresponding to every xy in W1, so let me just designate these sectors by W1, W2, W3, W. So we have defined W1. Define W1 W2 as, this is the upper wedge that you have, this is W2, this is W3 and this is W2. Okay. What is W2? W2 is y greater than or equal to 0, and you have mod y or mod x is less than or equal to 1. Third one, W3 such that what you have is y also could take negative values. So you have mod y then you have W3, W4, W4 is such that y is negative, and what you have is mod x these are the four regions that you have: W1, W2, W3, W4. So you see that there is the relationship between W2, W4 and W1 and W3. What is it? W3 is essentially the reflection of W1 through 0, 0. And you can get W1 from, or W3 from W1. Okay. It's a map from and R inverse is given by R. Similarly, W4 is the reflection of W2 through zero, and what you have is R from and of course R inverse is equal to so that is well defined. And now what do you infer? You infer that given an element of W3 okay, now we also want to look at this map. Use a map called inversion. Okay, so let me draw some picture here. This is inversion. Take some xy. This is the map R. So you have reflection all over. Okay, this is mapped into this. Similarly, the point here is mapped. This is also R. So R maps are happening in this space. Now we introduce another map. W1. Then define X. Okay, so let me define it this way. W1 with the both W2 by I plus of xy okay. Right. Then you see that if then we observe that the following phi of this is in general true. Why? Because it's all the symmetry. So this relation we have. Okay. Therefore, yeah, we'll come to this. Also, phi of is also equal to these two results we have, because change x to minus x, y to minus y, you get this result. Change x to y and y to x, you get this result. And you see that this operation is actually this I plus operation is essentially reflection on this. Similarly, if you write I minus, okay, we will come to that. So let us define W2 plus as that is, they belong to the first column. Similarly, you have W2 minus that such that what do you have? So you have it is W2 minus. So this is W2 plus minus, and this is W3 plus both x and y are x is less than or equal to 0, y is greater than or equal to 0, it is in W2. Okay. Now W3 plus defined as W3 is this. Okay. Now there what you have is yeah, okay. Y is yes, this is the definition. Therefore what you have, so define I minus I minus xy to be Now what is that point? That point is y minus y x is positive, therefore sorry, x is negative. Okay, x is positive here, so you want this to be minus. So y is positive, x is negative. Yes. Yeah. So y is positive. Minus y. X is already negative, so that is to be this. This is the inversion. Okay, so this is reflection on so we have got that. Now what I want to prove is the following. Okay. Now you see that using these maps one can prove that there exists or rather I'll say V there exists belong to W1, W2, W3 and W4 such that okay, we use all these properties that if xy gets mapped to UV then minus x, so all that we need to prove is this. And then you also have That means you have a, sort of one-to-one onto maps between W1, W2, W3 and W4. Okay, such that once a UV is given, there exists 4 points in the XY plane which gets mapped to. Has its image. That's quite easy to prove, because you see that if UV is here, XY is here, then YX is here. Okay, so in W2 there is a element, and then minus X minus Y is here, which also gets mapped to the same thing. Then you take this reflection on this one, and that's also, that is what you get, minus Y minus X. Okay, minus Y minus X is also getting mapped to B plus. Sorry. I think I'll take out this line, and then there are some more things. I'll correct it. There exists 4 points. That's the position. Now we will make it more precise. The precise statement that you can make is that, okay, so we will make this statement precise. More precisely, there exists belonging to XY, 1 each to U. This is quite easy to see. If UV is here, then there is an XY here, that we have seen. Reflected. YX gets mapped to the same point. Okay. Now what you do? You take XY and take minus x minus y. Minus x minus y, if xy is in W1, then minus x minus y is in W3. So that also gets mapped to the same point. Okay, so let us start with this. So for instance, I'll just for example, if B plus, then there exists xy plus such that UV. Consequently, what you have, therefore, where is xy? Xy now is in W1 plus. Okay. Therefore, now reflect it along this line. So you have, there exists yx which belongs to W2. Okay. Such that now what do? You take the reflection of xy. Minus x minus y gets mapped to UV, where W3. Similarly, where is this? Minus y minus x also get mapped to UV, where W4. That is because this is, I will draw the picture. So this is what I have. So corresponding to UV, this is x equal to y, x equal to minus 1. So corresponding to UV, there is a, then its reflection here, this is y x. Okay, so this is w1, this is w2, this is w3, and this is w4. So minus x minus y is in w3. And what about this? This is minus y minus x. Minus y minus x is now in w4. This is w4. This is w3. This is w1. Okay. Right? So you see that, and similarly, hence we have is not precisely for each xy belonging to V, there exists 4 points, one each whose image under phi is so this is what we have proved so far.